So in this lecture, we're going to look at stereochemistry of the Diels-Alder reaction along with electrocyclization reactions. This is going to be technically a review from organic chemistry 2, but I feel like as far as things that are important but are hard to hang on to when time goes by, this is up there. So anyway, stereochemistry in the Diels-Alder reaction. Okay, so all of this, underpinning all of this are the Woodward-Hoffmann rules. The Woodward-Hoffmann rules, it's one of these. This is a topic that could really encompass the bulk of an entire advanced organic chemistry course, but to suffice it to say that for pericyclic reactions, which is what we've been studying this week, orbitals must interact and maintain symmetry. And what I mean by interact is orbitals must overlap with the appropriate phase. Okay, and so sometimes this is called in-phase overlap. And what I'm referring to is when we have orbital overlap that's like head-to-head or something. What we had talked about a lot in this unit within organic chemistry 2 is that if you've got two orbitals that are pi orbitals, you want these things to interact so that we have either white on white interaction or dark on dark interaction. The white and the light and the dark just represent either positive or negative lobes. So you could define them in either way. So you could have the dark be the positive lobe, the light be the positive lobe, whatever, just as long as the two lobes are different from one another. And just so happened that with pen and paper, it was easy enough just to leave one shaded and one unshaded. Okay. So this was a really big deal. This is a really big deal for pericyclic reactions because before we understood the Woodward-Hoffmann rules, we had no idea why pericyclic reactions were occurring. Again, we didn't have some sort of positive negative attraction here. We mostly had just carbon atoms grouping together, and it just happened to work better when we had pi bonds present. Now what we know is that when we have pi bonds present, we have unhybridized p orbitals that are a little bit more accessible for overlap. And so another way of thinking about this is to consider only two sets of orbitals interacting with each other during the course of the reaction, and that is the Homo and Lubo orbitals. So for the most part, the interacting orbitals are the Homo and Lumo, where Homo is highest occupied molecular orbital, Lumo is lowest unoccupied. So there's H and O, and then we have lowest unoccupied. And this way of envisioning the molecules is we're looking at delocalized molecular orbitals. That is, areas with which electrons can exist that are distributed throughout the entire molecule and not localized to a single atom. That's one particularly popular approach to studying molecules, and it's very helpful for pericyclic reactions. Okay, so if we consider the Homo, what we would do instead of drawing our pi system of our diene like this, we would consider having 4 p orbitals. Now, these p orbitals can come with certain symmetries, and so depending on whether or not we're in psi 1, psi 2, psi 3, or psi 4, if you remember, we had these rules for building a molecular orbital diagram. And so if we consider the HOMO, that would be psi 2 with one node, and the one node is kind of slicing right through here. Psi 2 nodes equals 1. Now for the LUMO, which is just our alkene, our dienophile, that also has one node. And I'll just draw it this way, where we have a change in phase. So a node, let me remind us all, let me back up a second. A node is when we flip colors, I guess, going from light to dark. So this would be psi 2 here. Once again, nodes equals 1. It's just by coincidence that both of these are psi 1. Okay. So it's the interaction of these two molecular orbitals that allows for the formation of a Diels-Alder product. Okay, now in particular, what we could do is we could consider psi 2 of the diene. And that's going to have then 4 p orbitals. We could go shading this way and shading down this way. Remember, the choice of shading is arbitrary, just as long as one side is positive, one side is negative. And in this case, we have one node slicing right through the middle of the molecule. Now, what we could do is write psi 2 of the dienophile. And just to make sure I get this right, I'm going to put the shading on the bottom for the left side, shading on the top for the right side. Again, it could be on either side. We determine positive and negative. The important thing is that we have one node in either case. Now, if we align things this way and draw the orbitals this way, we could see how we could form a bond between the atom here and the atom here. So again, I'm going through this rapid speed compared to organic chemistry 2. So hopefully this is kind of coming back. But anyway, it's the interaction of these orbitals that controls the stereochemistry of the reaction. That is to say, if I had a complicated molecule like this, and I'm adding it to just some straight alkene or whatever for now, I would actually form, in this particular example, 2 stereocenters where I've got my atoms corresponding to the diene labeled as a dot in a circle. So we have a CH3 on both of these atoms, and the other one has a fluorine atom. So we don't have any sort of planes of symmetry here in this particular molecule. Each of those circled and starred carbons are chiral and have dash and wedge components with them. So how do we think about which stereoisomer would be preferentially formed? Well, what we do is we consider a perspective drawing where we can see the ends of the pi systems for both the diene and the dienophile. Now, I'd mentioned that if we go top and bottom, we would go bottom, then and top, and we could overlap these orbitals. So it's as if the diene is docking underneath, or excuse me, the dienophile is docking underneath the diene to form the bond. And then we have to do this weird relaxing. Now let's go ahead and draw that with some substituents. So I'm going to have, instead of my unhybridized p orbitals representing the molecular orbitals, I'm going to consider the groups attached to the alkene. Now in this case, I've got 2 groups that are sort of resting on the inside of the diene under this perspective. Then I've got another 2 groups that are sort of hanging out on the outside of the diene. And what we're going to do is consider what the stereochemical outcome is if I allow the molecule to interact, the diene and the dienophile to interact in this way. And when I do that, I'm going to get this outcome, if you remember. So here are my arrows. And I have this really weird looking molecule that results from this. I'm going to put my methyl group and fluorine sort of poised over top of the ring, and then my methyl group on the fluorine center hanging out along with the hydrogen on the opposite stereocenter hanging out. Now, this is kind of tricky to see. There's a CH3 group there. Now, this is perfectly an appropriate drawing, but we should relax this so we can get to a top view structure. And I should also consider my pi bond in the back here. So I'm going to relax this, and this is where I unfold it. So I've got my fluorine and my methyl group, and I'm just going to roll them out to open up the ring system and get to my flat two-dimensional perspective. Now, when I do that, the things that were hanging over top of the ring sprawl outwards and are now up. The things that were out are now down. At least that's my stereochemical model for understanding what's happening. So I put a fluorine going up and a CH3 going up. And then for every wedge, there's a dash. And there's my stereochemical outcome as controlled by the diene. Now, we haven't even talked about the dienophile. And to review that, I'm going to go ahead and just touch on the Endo Rule. So stereochemistry at the dienophile. Okay, this is where we come into the Endo Rule. So what the Endo Rule allows us to understand is what happens if we've got our diene interacting with a dienophile that's sufficiently complicated that we would then generate stereocenters in the Diels-Alder product. So if I draw this Diels-Alder product here, a six-membered ring with an alkene, now I have stereocenters at these positions, and I should think about which product is going to be formed. Well, we can consider two possible transition states. We can have the exo arrangement and the endo arrangement. And exo and endo come from how these things are positioned relative to the forming ring. So I'm going to once again consider my perspective drawing to show the formation of the ring system. And I use dashed lines to allow me to kind of see how the bonds are being formed. Now in the exo arrangement, we're going to take our stuff, and this works particularly well if our stuff has pi bonds, and we position it outside the forming ring or exiting the forming ring, whereas in the case of the Endo Rule, it's underneath or inside the forming ring. It's kind of a sloppy drawing, but hopefully it's coming back at least a little bit. Now it turns out that the endo product is kinetically preferred. That is, in terms of what's forming most quickly, it's the endo product that forms most quickly. So this is formed the fastest. Now when we draw the resulting product there, the important thing is not necessarily to get the stuff underneath right, but it's to get these two hydrogens right. Because when we unfold the ring, we're going to tilt those upwards, and that's going to give rise to a product where the hydrogens are wedges. The hydrogens are wedges to each other, and then the carbons, I'm going to throw the dashes on top of these carbons. The carbons are then dashes. So the Endo Rule, again, this is an unusual situation because the Endo Rule is kinetically the fastest situation, or the fastest product that's formed. So it's the kinetic product. Now, what's unusual about this is it's not the most stable product because of steric hindrance. Everything's trying to fit underneath the growing ring. Instead, the exo product, and I could draw the outcome there quickly, the exo product is the preferred product, and you could, sorry, I'm jumping a step here. The exo product has less steric hindrance, and you might say, well, aren't they the same? They are the same in this case, but let's let that slide here, okay? We're just trying to get endo and exo back in front of us. But the exo product, the exo transition state, is the thermodynamic transition state. That is, it generally leads to the more stable product. It turns out, though, that in this particular example, there's several examples like this, but they're not the majority by far. But in this particular example, and many others, but not the majority, the kinetic and the thermodynamic products are different. The exo product is the thermodynamic product. It's most stable energetically, whereas the kinetic product is formed most quickly, but the two are not the same. Now that's unusual. If you are forming the kinetic product quickly and you'd rather have the thermodynamic product, one thing you could do is heat the reaction up really high temperatures, force the reverse reaction to occur by way of a retro Diels Alder, which we talked about last time. And then eventually you'll kind of collapse the energy difference between the two transition states and force the equilibrium back towards the more thermodynamically stable product, which is the exo product. Okay, so what I want to do is we'll touch on the stereochemistry of electrocyclization reactions in the next lecture. I feel like I've gotten enough long-winded in this one to merit kind of cutting the video here. So anyway, I'll see you in the next lecture.